Hello, everyone. Good day, good evening, or good afternoon, or good morning, wherever you are in the world. My name is Rommel R, and I am from the University of the Philippines, Mindanao, and I'm here to give an introductory course to inverse problems. The rigor is meant to be for beginning master students. Yeah, so that's why I want to make it introductory. And also want to acknowledge also my University of the Philippines, Mindanao, SIMPA and ICTP, who made this fellowship possible, as long as with CIRM for hosting me this week. Okay, so again, I'm currently doing a fellowship, so this is part of it. And how do we see the course for the next 8 hours in total? So, because it's introductory, I'll focus more on the depth. So we'll start with examples of inverse problems to give us a motivation on the importance of this class of problems, especially in applications. Then we'll go a quick tour on important concepts from analysis, in particular in Banach spaces and Hilbert spaces. And then in this lecture, we will focus on two methods. First, Tikhonov regularization and the Landweber iteration, two of the most basic regularization methods, which I believe is a good start for learning inverse problems, in particular in regularization theory. So first, I want to acknowledge that this lecture is based on the course of inverse problems taught by my PhD supervisor, Chin Yan Jin, from the Australian National University, where I also got my PhD, and can also access the lecture notes or slides that I'm using here on my website. So it's all there. And first, let's talk about what do we mean with inverse problems. So the idea of inverse problems imply the idea of a related problem. Okay, and so there's like a relationship between these two problems. So first of all, J.B. Keller back in 1976 gives us this formal definition of inverse problems. So when we have two problems, they are inverses of one another if the formulation of each involves all or part of the solution of the other. And for historical reasons, the direct problem is something that has been studied for a much longer time already. And then later on, mathematicians got more concerned on what if we solve the inverse of this direct problem? Okay, so normally we call the former problem as the direct problem, while the latter is called the inverse problem. And that will be the focus of this lecture here. So first, a little definition, which we will see a lot. When you have a problem, we describe it as well-posed in Hadamard sense if it satisfies three things. First, the problem has a solution, it has a unique solution, and the solution depends continuously on the data. The third one means that if there are small changes on your data, then it must also lead to also small changes in the solution. If one of these requirements is violated, then we have an ill-posed problem. For instance, in the third condition, a problem is ill-posed if there's an instance that a slight change in the delta, or rather in the data, can lead to very drastic changes in the solution. And also, usually the direct problem is the well-posed problem. And what makes inverse problems an interesting area to study on is that they are ill-posed. We will see later. And here's an example, a classic example of inverse and direct problem, which is something that you know in calculus, which is the integration, differentiation. We know integration is the inverse, the differentiation, and vice versa. If you have an integration problem, you need to find, for a given function f, you need to find the integral, the function f. And the differentiation problem is to derive the derivative of, denoted by phi, such that phi is equal to f prime, which is the derivative of f for the given function f. And by the fundamental theorem of calculus, we can formulate this equation in this way. Now, we will see that integration is a well-posed problem. However, differentiation in general is ill-posed. And let me just breeze through this example. So for instance, let's consider a continuous function f from -1 to 1. And let's consider a perturbed function with respect to f, where we add to our exact function f some perturbation delta times this sine of x over delta squared. So this is our perturbed data. And then if you compute the infinity norm of the function f, then of course it's easy to see that the infinity norm of the difference of f and f delta is equal to delta. And if you do the same for the derivative of the perturbed f and the exact function f by calculus, you can derive that taking the infinity norm, it will be equal to this 1. And of course, the maximum of this cosine is equal to 1, so we have 1 over delta. Okay? So the point here is that for our given function f, the perturbation is quantified by delta. On the other hand, the perturbation of their respective derivatives is 1 over delta. Now, as you can see, we can make f delta as close to f as close as we want. So that is when we let delta be close to 0. However, if f delta gets close to f, then the error between the respective derivatives can be arbitrarily large, because 1 over delta blows up as delta goes to 0. And this tells us that differentiation is an inverse problem. And in particular, we interchange it when we say inverse problems and ill-posed problem. When we say ill-posed problems, then we actually refer to some inverse of a given problem. Now, so in that example, let's try to consider an important instance. Now, suppose you don't know f, and you only know f delta. Oops. Wait, I'll just, sorry about that. Let me just, so example here. Suppose if you don't know f, and suppose you only know the noisy information of delta, and suppose you also know the error level delta. Now, the question now is, can we find an approximation of f prime using f delta, not f, okay? So to this end, we will use a familiar difference equation to us, which is the central difference coefficient of f delta, which is given by this one. So now let's consider how well the central difference quotient approximates the derivative f prime. So by calculus, we can actually expand this one by using the definition here, and then I'll just not go to the details here, but the point here is that by adding and subtracting some terms, and then you take the bound of this one by triangle inequality, and then I will let you show that this is, in fact, these first two terms here is just less than or equal to delta over h plus this one here. So notice the first term here is in terms of delta, which is our noise. And this one, if you look at the second term, is actually the error between the center difference and the exact f prime. Okay? And if you look at the first term here, notice we are actually computing the difference between f delta and f, and also f delta here and then f over there. And then in order to describe this error, we also need to some a priori information on the smoothness on f. So for instance, let's say if f is a C2 function, note this is an a priori information. That means it's an information that we know before we proceed with computing the approximations. That by Taylor's expansion, we can expand f of x plus h and f of x minus h in this way. And then if you compute this quotient here using the Taylor expansion, then this will be equal to, and then before that, if you subtract it to f prime of x, this will be equal to this one. And then you take the bound on both sides and use the definition of the infinity norm of the third derivative of f, then you will have this much more useful bound of the center difference approximation and the exact and inaccessible f prime. And then, as you can see here, to find a useful estimate of this error, let's try to choose h to be somewhere around delta to the 1/3. Then by going to the computations here, you can also show that the difference is of big O of delta raised to 2/3. Okay, so I'll just breeze through this example here. So also we can also assume that f prime is in C alpha. So that means there is some constant C sub f depending on f prime, so that we have this bound over here between f prime of x, between 2 points x1 and x2. And then we say that f prime is also continuous with exponent alpha. And then by fundamental theorem of calculus, we will have this one. And then by breezing through the computations here, we don't have to go to every detail here. So we can actually see that in general, the approximation error is of order delta of alpha over 1 plus alpha. Now, what is alpha there? That's actually the parameter that controls the smoothness of the function f alpha. Okay? So if you look at this one, this tells us that the error between the center difference and f prime is of order of delta of alpha over 1 plus alpha. In fact, we can actually show that earlier this delta 2/3 is actually it's of optimal order. That means if you consider the values of alpha here, then we can actually see that the maximum is obtained at alpha over 1 plus alpha. Okay? And also note this one, if you let h be approximately delta over 1 plus alpha, then we will have this one here. Now notice that in this example, we're taking h approximately something like a multiple, or simply the error delta raised to 1 over 1 plus alpha. And let's see what happens if it computes the derivative of these two functions here. So in the first simulation, we have the derivative. So let's see the actual approximation using the center difference in approximating f prime. Later on, we will see if delta, given delta is equal to 0.01, and then we'll choose several different values of h. In the second one, we'll do the same thing, but here we will use an absolute value function of x, which we know is not differentiable at 0. That's why it's discontinuous at 0. So I'll just let you go through the plots here. So notice what happens if h equals 0.5. Notice from left to right, we try to decrease the step size h. If you've done finite differences, you probably know that the smaller the h, the better the approximation, but not quite. Because notice what happens if I take a much smaller value of h. Notice that the approximation gets worse. For instance, here h equals 0.02, it gets much worse compared from h equals 0.06. And the same can also be observed in these values, in the absolute value, which is a step function here. In fact, the derivative, I forgot to mention that what we're actually approximating is not f, but the derivative f prime. That's why f prime plus 4x cubed looks like this. And also earlier, if you look at the absolute value of x, its derivative is f prime of x equals sine of x. And then that's why the f prime looks like this. As you can see also, from left to right, from up to down, notice that as we make our h much smaller, notice it approximates better the function, although we could do much better by approximating this non-smooth part here. But notice if I take smaller step sizes h, notice our approximation blows up. It gets more oscillatory values here. So to summarize this observation here, high frequency error can be amplified by direct differentiation. And then we can introduce a family of functions depending on a parameter h. And notice from the previous examples, a reasonable approximate of the derivative can be obtained by choosing the step size h carefully. But how to choose an optimal h is a challenge in itself. And a priori information can improve the accuracy of the approximation. Notice this information may not be easy to verify. So sometimes you just assume and try to see if it works. And then note that loss of information cannot be avoided. And that's the important property of the inverse problems. Let me go back to the approximation error again. Notice this tells us that you cannot really compute the exact derivative by the unknown derivative f prime by the center differences without any error. But you can only get something close to it by choosing a suitable step size h. Okay? And now so from simple calculus problems, let's go to an example. So the next one is a classic type of inverse problem, which is called the inverse source problem. So let's consider an object of unit mass moving along a straight line, and then suppose it also forgot to mention that it's under a time-dependent force f of t, and let's assume that its initial position is at the origin and its velocity is 0. And then by Newton's second law of motion, the position u of t of the object at an instant t obeys the following second order differential equation. So you have the differential equation here, and you have the initial condition here. So the direct problem is, of course, given the time-dependent force f of t, you compute u. And on the other hand, the inverse problem is, given the measurements of the position of the object, you want to reconstruct the force function f of t for all t in this given interval. And in fact, this is an ill-posed problem. And let me just go through why it's an inverse problem. In fact, by going through the integration of this one, you can actually solve this is equal to this one. So if u of t equals this integral here, then by simple change of variables, this will be equal to this one. And in fact, you can obtain u of t as the Volterra equation of the second kind. Okay, so that's an example of an inverse source problem. Now, what I want to focus more is an important example of inverse problem, which is very well studied, especially in applications, especially in medical imaging, which is about the X-ray tomography. And how does it look like? It's this one. So suppose we have an inverse problem of determining a function f of two-dimensional cross section omega of a human body by measuring the attenuation of the X-rays. So it's like this. So let me just draw it here. Okay, so suppose let's consider a two-dimensional cross-section. Suppose it's like this. And in an X-ray, you usually have an emitter, and then you have a detector. So X-ray travel across along the line. So from the emitter, an X-ray is defended to here, and it's being detected here. And suppose this is our omega. In this case, it's our omega. Okay, and then suppose the f over there. Let's consider it, but here instead of omega, maybe I'll just use a different notation here. Let's say d, and f here. Suppose that's the density of d, and normally it's spatially varying, so it has different values across this region here. And then the inverse problem here is we want to recover the F, which is the density, based on the X-ray measurements. Okay? And how do we do that? Is by using what is being we describe here. So we parameterize these lines, which describes the travel of the X-ray by, let's say, the unit normal vector. So let's say that's this one. And let's call that omega. Okay? And suppose that it's the origin, suppose the distance is s. Okay? And then we also parameterize it by the, that's the vector perpendicular to omega, so that's omega perp. So therefore, and suppose this distance is equal to t, so s times omega plus t times omega perp parameterizes every point on the line. Okay? And now we denote I by the intensity of the X-ray beams. So that's our model there. And then let's have an assumption, which has some physical interpretation as well. Let's assume that the intensity of an X-ray beam along a distance delta t is proportional to the intensity I, the density F, and delta t. Therefore, this difference equation of the intensity is equal to the negative because we have we're measuring the decay, so negative of the intensity at every point in the line where the X-ray travels, and times the density of at that line over there times delta t. And then if we let delta t approach 0, then we have this difference equation here. Okay? And as you can see, if you let I sub 0 be the intensity of the X-ray beam at the emitter, and I sub 1 be the intensity at the detector, then it's easy to see that you can write that differential equation like this. That's di over dt over s omega plus t omega perp divided by intensity dw perp, and that's equal to r minus f. Yeah, it should be like that. Okay. Then if you integrate both sides, then we have that final equation there where we have to take the logarithms here. So we have log of I1 of s omega minus log of the intensity at the detector equals this integral over here. And that integral is actually gives us the integral of the function f along the line. And in particular, we have a name for that function there. So you can see the definition. The integral of f along the line is called the Radon transform of f. So therefore, the inverse problem can be formulated like this, where suppose given the random transform, is just write that one. That's a log. Oh, sorry, that's I messed up with my logs. Sorry about that. So you have minus. Yeah, that one. I1. That should be I1. So the inverse problem can be compactly expressed in terms of the random transform, where given the intensities of f of the X-ray, you want to reconstruct f. So notice this one here represents the X-ray measurements being recorded from here and here. And in particular medical imaging, reconstructing F gives us an information of the cross section of the human body. Let's say also it can give us information whether, let's say, there is a tumor, let's say in a brain scan. Okay, and then now let's show why is this problem an ill-posed problem. So now let's consider a very special case. Let's suppose omega is actually a circle, something like this. So let me just write it here. It was a circle with radius 1. That looks bad. Okay, and then suppose f is radial symmetric. That means f of x is equal to the value of a single variable function, capital F, taken at the norm of x. And then it suffices to use x-rays parallel to the x-axis. Okay, so suppose all the x-rays parallel on lines parallel to the x-axis, and let's only consider omega O as 0 to the plus minus 1. So that means this is the normal of all the x-rays being considered here. Okay, so what happens here is to parameterize this one. It will look like this. So suppose example given in our example there. So this will be my x. So this is distance of s. That's the origin. This is t. So therefore, every point here, as usual, it's that x equals s omega o plus t omega o perp. So therefore, our random transform is something like this. S omega, that's the integral of, let's just write it again, f of s omega plus t perp dt. Oops, could have used more. There's the space there. Now, if you look at this one, t here is the distance that goes through goes along the X-ray, and not more importantly, look at that we are integrating f along the line at the point along the line. That's denoted by t. That's why we say the random transform is the integral of f along this line, which represents the paths of the x-rays. And then, so from this one, we can use a change of variable here. So we can let tau is, or actually we can just let s squared plus t squared equals 1. Okay. And then we can use this, sorry, that should be tau over there. Let me just, let me just check. And then what we can actually see here is that we can solve for t. And t is just plus minus square root of 1 minus s squared. That means that's here from here. So that means we can simplify this integral further by simply computing the integral from the minus of this one up to the plus. Okay, so therefore we can write s omega o as the integral from minus square root of 1 minus s squared, then plus square root of 1 minus s squared. And then we can now use the property of f being radial symmetric, because we can actually show that if you look at this point here, this is a point in R2. And then by using that property, that's just equal of f of s squared plus t squared times dt. Okay, and then by change of variable here, leave it to you guys. If you let this one equal to tau, then you will get another version of the Radon transform there. And then, so therefore, if you look at the problem here, the determination of f can be obtained by solving this Abel integral equation, which is equal to this one over here. And in fact, I will not just go into the details here, that we can actually compute explicitly the solution of the Abel equation, which is equal to this one. In fact, by a lot of computations here, you can actually show that f of t can be expressed explicitly at this one. Now, if you look at this one, notice that the computation of f actually involves computing the derivative. And we know previously that computing the derivative is an ill-posed problem. And that's why the problem of X-ray tomography is also an ill-posed problem. So that's something about that we need to know about the inverse problems. So as you can see, a lot of them involves the standard stuff from calculus, differentiation, and integration. In fact, this particular problem here is an integral equation. In fact, we can actually see that many inverse problems can be reduced by solving the integral equation of the following form, where omega and d are domains in Rn, k of xy is a given function called kernel, and this kind of equation is called the Fredholm equation of the first kind. Now, because we want to find how to compute solutions to inverse problems in a in a stable way, we need to specify on which solution space are we going to solve the equation. And before we proceed to how to compute the solutions of these equations in a nice way, when I mean in a nice way, that means we are sure that's the best approximate that we can actually get. And then that leads us to going through some important concepts from analysis, which I will just go through everyone. So I will focus on a lot of important stuff here. So at this point, I'll just skip the first few parts. Assume you already know a little bit of calculus. If you miss some details, of course, you can always go back to any standard linear algebra or analysis textbook. But we'll just go through this notation so that later on we will be familiar with the notations and all that we need. Okay, so first, throughout here, we start with a linear space X, which is just another term for a vector space. So first, we know that vector complex or real linear space, actually here we just consider real vector spaces, and we can also consider a norm on X which has the following properties. And normally we'll consider a linear space X equipped with a norm. So we have a norm space, so it satisfies these three properties. Of course, the norm is positive, it's homogeneous, and it satisfies the triangle inequality. And also we denote the norm as the distance between the two elements, which is denoted by this one, the norm of X minus Y, very familiar notation. Now, we also need to define briefly what do you mean with the convergence. So a sequence X sub n is convergent if the norm of the distances between the X and the sequence is 0. So that's the limit. And we call X the limit of the sequence X sub n. And throughout, we denote that relationship in the following notation here. And we know from calculus that the limit of a convergent sequence, if it exists, it must be unique. And also, an important sequence throughout the discussion is about the Cauchy sequences, which a sequence where it gets closer and closer to each other. And we know that any convergent sequence is a Cauchy sequence. Okay, and also I'll just skip to these examples here, especially for Banach spaces. After all, we will consider Banach spaces, so this is the inner product. So an inner product is if you have a complex or real linear space, this function is called an inner product on X if it has the following properties. First, it's positive, it's symmetric, and it's linear, something like this. And then also, if X be a linear Hilbert space, then this allows us to express the norm of a vector as the square root of the inner product of the vector and itself. And then you can also show that the Cauchy-Schwarz inequality holds, very useful inequality later on. So make sure you remember that equality there. Assume you're familiar with it. Okay. Now, throughout in the course, we'll consider Hilbert spaces. Suppose we have a linear space with an inner product. We call it a pre-Hilbert space. If it's complete with respect to the norm, then we call it a Hilbert space. And then also, I'll just skip this part here, the parallel law. And then I'll just consider, I'll just keep some parts here. So that's about continuity. We also need some, because we're dealing with types of inverse problems with the linear operator, then we also define a linear operator in this way. And also we define that A is a continuous at X is an element of X if for any sequence converging to X with respect to their distances, then the same can be said with the distances between their respective values at A. And we say that A is continuous on X if it is continuous at every point in the space X. And also, A is called a bounded linear operator if it is linear and there exists a constancy such that this property holds. Okay. And a standard and useful result in analysis tells us that a linear operator is bounded if and only if it's continuous. And also, we denote also throughout the course with the norm of the two Banach spaces, which is equal to this one. And we call that the norm of the functional I. And here, suppose we consider any linear map F, we call it a linear functional. And note here, earlier we're we've shown the norm of points in the Hilbert or Banach space. Here we're considering the norm of a linear map F that maps from our space X to the complex space or the real space, the set of real numbers. Then we use norm of F to denote it, and that norm is just the supremo of the absolute value of F of X across the points on the unit circle. That's why you have norm of X equals to 1. Not unit circle actually, but all the points whose norm equals 1. Okay, and also, can skip this part as well. It's just the properties of linearity. We also need the idea of the adjoint. So, suppose you have a bounded linear operator A mapping two Hilbert spaces X and Y, and then we define the map A star with a mapping from Y to X that satisfies the following property, where in the left-hand side, we take the adjoint on the space X, and in the right-hand side, we are taking the inner product on the space Y. And we know that that is the adjoint operator of A. And then also, we can also show that same as A, the adjoint is also a bounded linear operator. And in fact, their operator norms are equal. And then also, more importantly, we'll also consider orthogonality. So we call two elements U and V orthogonal if their inner product is equal to 0. And we denote by U perp as the orthogonal complement of U in X. That means all the points in X orthogonal to every element in U. And also, we consider a sequence U sub n in X be an orthogonal basis if first the vectors are orthogonal. Okay, and in fact, I mean the vectors are this one. So that means the pairwise inner product, it's either 1 if we're taking the inner product of the vector with itself. Otherwise, the inner product of one of the elements in the basis to the other must be 0. And what's nice about the orthogonal basis is that first, if we can write every element in X as a span of the elements in the orthogonal basis, then we can exactly compute the scalars that we pair with every element in the basis, and that is in terms of the inner product of the X and every element in U sub n. And also, more conveniently, there holds this Parseval inequality, where the square of the norm of x is equal to the sum of the absolute values of the inner products of x and every element in the orthogonal basis. And also, a useful inequality, Bessel's inequality, where if you take an orthonormal basis in x with infinite number of elements, then for any x in x, then the infinite sum of the absolute magnitude of the inner products can be estimated by a useful upper bound, a much simpler upper bound, which is just given by the norm, or the square of the norm of x. And also, going throughout here in the notations here, if A is a bounded linear operator between two Hilbert spaces, then we define the null space of A as all the elements in the space egg, so that the value of the operator A at x is equals 0, and R of A as the range space or range of A, which is defined in this way. Okay, so that's simply all the elements in Y that can be expressed as in terms of A times x for some x in x. And we have this very useful relationship between the null space and the range of A with respect to the A in its adjoint and it's also the orthogonal projections. So let's take note of that one. Okay, and also we also need to define a bit about compact operators, but we can actually skip that one. Also the singular value composition. I just put them here because you might find it useful. So let's skip that one. And before that, also I want to mention that a lot of the concepts of this lecture is based on this reference here, which is the regularization of inverse problems. This book by Engel, Hanke, Heinz Engel, Martin Hanke, and Andres Neubauer, published back in 2000. It's the Bible of regularization theory, which is very important in solving inverse problems, both in the theory and the numerics aspects. And then now let's go deep. Suppose we have a compact linear operator A between two Hilbert spaces, x and y, suppose the singular value system. Then, if we go back to the singular value system, and that holds with a compact linear operator between two Hilbert x and y, then there exists a countable set of triples denoted by sigma n, u sub n, and vn with the following properties. First, sigma 1 and sigma 2 are arranged in this way, so sigma 1 is greater than sigma 2 and so on, and they're all positive. We denote sigma 1 as the norm of A, and if, let's say, the dimension of the range of A is infinity, then the limit of sigma n as n goes to infinity must be 0, so that means the singular values decay. And u sub n, denoted as the orthonormal basis of n of A perp. V sub n is an orthonormal basis of n of A star perp. Note, when you say orthonormal basis, that means the set of vectors are orthogonal and each vector has a norm 1. And also, we also note that u sub n as the right singular vectors and v sub n as the left singular vectors of I. Okay, so let me just go through this one. So, by orthogonal decomposition theorem, we can write x being x as equal to the sum of x sub o and x perp, where x sub o is an element in n of A and x perp, using the basis on the n of the orthogonal complement of n of A perp. That's from the singular value system here. Then we have this one. And then by using the property of singular value, the system can write a times x equal to this one, and a star a of x is equal to this one. So notice here, every time you multiply both sides by a star of a star, notice we have an exponent here, sigma n square. And then we have this inner product of x and un times un. Okay? Now we can extend this earlier by multiplying a times a star a k times. And by induction, we can show that a star a times k raised to k of x is equal to this sum over here. In fact, we can generalize this further, that by considering any polynomial p of lambda, which is denoted by this one, that holds the following. So I'll just keep this computations here. And the point is that we can describe a function of the operator a star a, which is a self-adjoint, because notice the adjoint of a star a is itself. And then if we let f be a continuous function defined on this norm here, then we define f of a star a, that's by x to x. So that's from here. Note this is a self-adjoint. And we will see this a lot later on. And also, it's easy to see that f of a star a, which is defined here, it's a bounded linear operator, and we have this very important result where the norm of this bounded linear operator f of a star of a is bounded above by the supremum of f, where lambda is taken from 0 to the square of the norm of a. And I'll just breeze through this important lemma here, which we don't need to prove. If you want to check the proof of this one, you can go back to the reference. Okay, so the point is that if f of a star, which is a bounded linear operator, if you multiply it a on the right, then that's equal to multiplying a on the left of f of a star a. Now note the sequence of the multiplication of a and a star. Okay, and the same thing here, just replace a by a star, you will get this one. So the idea is that when you move a from right to left, the order of the taking the adjoint and the operator changes. Okay, and also we have this very important result, which is the interpolation inequality, which is equal to this one here, which is very useful in approximating errors later on. And we will, so just remember how this inequality holds, but we will see it in action later on. Okay, so maybe just a little break before we go to the next